Hi, my name is Osama Nasir, and I'm a PhD student at Brown University. I'm delighted to be virtually here with you today and present our work on disruption-free update releases at Facebook. Software update is a part and parcel of modern infrastructures. Their workflow involves writing new code or configuration, releasing it to the globally distributed proxies and servers, and then restarting the corresponding components to update the old binaries or configuration. The updates and the corresponding restarts are essential for adding new features, fixing bugs, and upgrading security. Owing to the hundreds of services and tens of thousands of developers constantly pushing new code, proxies and servers are constantly restarted at Facebook. As shown in the figure, the proxy servers are restarted 3 to 4 times a week, whereas application servers are restarted hundreds of times a week. This roughly translates to every 2 hours every day. The fast pace is due to the adoption of continuous release philosophy, where code changes are pushed to the production deployments as soon as possible. The philosophy of continuous release is not unique to Facebook only. In recent years, we have observed adoption of this principle by companies like Yelp, eBay, Uber, among others. Although the problem is faced by many companies, we observe that the most commonly used solutions are built around ad hoc strategies. Most teams still resort to using the old days sleep and fail health checks routine. A restarting instance enters a draining mode where it fails health checks and consequently receives no new connections. The goal of draining is to organically conclude existing connections or gracefully shut them down. After waiting for this pre-configured training duration, the instant restarts and is initialized with the new code. It then starts responding to the health checks and the updated instance starts serving traffic. Such ad hoc approaches are suboptimal along multiple axes. First, there is a reduced availability as a restarting instance failed health checks. Second, at Facebook scale, we observe that a significant number of connections outlive the training period and hence are terminated. This effect is shown in the figure where there is a surge in the number of new connections at the end of training. Additionally, there's an overhead of rebuilding the state for such terminated connection. Third, the existing solutions do not generalize across protocols. For example, MQTT is a publish subscribe protocol and is used for services like Messenger. This protocol lacks graceful shutdown and faces disruption at the restart events. I'll further talk about the UDP limitation in the upcoming slides. Hence, there's either a downtime or disruption associated with restarts. Now, a general question is that what extent of downtime or disruption is acceptable to Facebook? From an operator's perspective, this depends on the type of deployments. For example, downtime for even a small number of machines can impact performance at resource-constrained edge or in ISP deployments, whereas the over-provisioned data center have more flexibility. From a user's perspective, this bound depends on the type of product or the service. Since Facebook strives for delivering the optimal performance to the user, ideally, any downtime or disruption should be transparent to the user. A restart that results in violating this transparency clause by introducing timeouts for connections or HTTP errors is considered to be disruptive. Now, with so many negative implications and risks associated with the release, the question is how to release the update while ensuring zero downtime and no disruption. Next, I'll give a brief overview of the infrastructure and identify the insights that can help in answering this question. Facebook infrastructure comprises globally distributed edge POPs and data centers. At each deployment, a fleet of layer 7 load balancers called proxygen manage the traffic. Proxygen at edge terminates the end user connection and forward the request to data center. Proxygen at data center forward it to one of the application servers. Hence, there's a hierarchy between the components in the layered architecture. Further, we observe that there is a single organization control over the end-to-end infrastructure. Hence, there's an opportunity to coordinate the connection workflows within and across the components in clusters. Based on these properties, the intuition behind zero downtime release is to leverage proxygen position in the end-to-end hierarchy to coordinate the restarts and prevent any possible disruptions. In the rest of the talk, we'll see interaction between two characters to enable zero downtime release. The first is a restarting proxy or application server and is represented by a house on fire. The second character is a proxygen instance. Like a fireman to a burning house, this proxygen collector will help in getting the restarting component out of trouble and prevent or mask any disruptions. Next, I'll talk about the details of how zero downtime is achieved for proxygen restarts. The idea behind eliminating downtime at proxygen restart is to initiate a parallel instance with the new code. The new instance further take over the sockets responsible for listening to TCP connection and receiving UDP packets. The new instance thus assumes the responsibility of serving new connection and the older instance enters a draining mode. This ability to take over socket has been added to other proxies like HA proxy and Envoy in the past few years. However, they fall short once we look at the connection state for protocol like Quick. Each connection has some associated application state. The older instance contains the state for the older connection, while the newer instance manages new connection and their state. If you look at TCP, the packets natively make their way to the right instance since kernel knows about their respective accepted sockets. However, we observe a problem here for UDP. UDP lacks any listening sockets, and the new instance takes over all the sockets responsible for receiving UDP packets. While UDP is connectionless, protocols like QUIC built on top of UDP do maintain state. Taking over the UDP socket will lead to the new instance receiving packets for the new as well as the older QUIC connections. Since the new instance does not hold state for these older connections, they will be terminated. To tackle this problem, socket takeover coordinates the packet forwarding between the two instances. Each instance has a unique ID, and that ID is encoded in QUIC connection packet as the connection ID. The new instance fronts the older one for QUIC, and whenever it receives a QUIC packet, it checks the connection ID to make the forwarding decision. If the connection ID matches the ID of the new instance, it will consume the packet. Otherwise, the packets will be forwarded to the older instance in user space. Now, to an outside observer, the machine that houses the two proxy instances is always available to serve a new connection. Hence, zero downtime is achieved without any disruptions. Next, let's see what happens once the draining period ends. As mentioned earlier, connection for published services that use MQTT protocol often outlive the draining period and face abrupt terminations. However, these connections have a unique property. They are stateless with respect to the proxy at a data center. In simple words, the proxy at a data center only relay the MQTT packets between the edge and the backend. As long as the packets for the specific user are making their way to the right backends, it does not really matter which proxy then relays the packets. The second technique, called downstream connection reuse, builds on this property and leverages a downstream proxy at edge to relay the MQTT packets through a different proxy at data center. The process requires implementing a solicitation mechanism through which the two proxies can interact with each other and initiate the transfer. As a result, the restart is transparent, and both the end user connection and backend state for the connection is preserved. Note that the proxy in a data center is an ideal scenario for this mechanism. In case of a proxy restart at edge, there's no similar downstream component available to maneuver the disruptions. For edge, Facebook relies on proactive reconnection, especially when the connection is idle, to mitigate disruption in case of a restart at edge. Next, we move on to how disruption-free restarts are achieved at application servers in data center. Similar to the proxy case, some requests may outlive the draining period when an application server restarts. HTTP post upload was specifically a major pain point for Facebook, as their associated data is uploaded over high RTT wide area network, and they often outlive the draining. Partial post replay is a novel HTTP mechanism through which a restarting server signals its restart intent to a downstream proxy. At the same time, it also sends back the incomplete post data it has received yet. The proxy reconstructs the request and replays it to another server. Once the request is completed, the success code is sent back to the user. Next, I'll talk about some lessons from experience. The zero downtime release has been functional at Facebook for several years and has gone through multiple iterations. In the paper, we mentioned multiple war stories and unintuitive scenarios where even rolling back to stable code does not work. Here, I'll focus on just one. A pitfall of socket takeover is that it introduces the possibility of leaking sockets and their associated resources. We faced a scenario where a faulty release led to some compatibility problems between the two proxy instances at socket takeover. The updated instance was expecting a smaller number of sockets than the one owned by the older instance. As a result, some of the sockets were ignored. When sockets are taken over, the kernel increases its reference count. Hence, although these orphan sockets were ignored by the new instance, they were functioning in kernel views and still receiving their fair share of packets. There was a severe outage, and machines in order of hundreds were affected. Millions of connections suffered from timeouts since proxy was not reading data from the orphan sockets. To tackle these issues, we recommend a strict monitoring of the sockets within the system. The proxy should monitor metrics like queue lengths, failure counts, etc. It's also essential that the receiving process acts upon each of the received sockets, either by listening on these sockets or by closing any unused ones. We further recommend adding a kill switch to the proxy to disable socket takeover at shutdown or restart. Finally, I'll conclude the talk by summarizing that Facebook leverages the existence of proxy hierarchy in the end-to-end path of a request to prevent or mask disruption. I'll end the talk with a question. How can eBPF help in further improving this zero downtime release mechanism? If you want to know the answer to this question or talk about it, please come to us. Thank you.
So I think that was a great talk. I'm waiting for questions on Slack. Please do post them as you have them. But just to get the discussion started, I actually found this whole discussion on Quick quite interesting, right? So when you did the socket takeover, you talked about state needing to be considered with UDP and Quick kind of changing that. So it struck me that this could be a broader question, as Quick gets deployed. So there are lots of stateful middle boxes and so on. And presumably these sorts of questions might appear in those contexts too. So do you have any thoughts on what this means for Quick in general? Might we need to start thinking about the middle box problem or state problem more generally for Quick?
I think that like Quick provides us an opportunity where everything is happening in the user space. There's more flexibility, and there's an opportunity to bake in more of these mechanisms in protocols from a user space perspective. I guess Luca will have more thoughts on it because he has actually implemented most of the stuff.
Yeah, so for Quick, actually, you mentioned middle boxes. One of the goals of Quick is to it being transparent to middle boxes, and there is just there are just a few fields that are exposed to the middle boxes, and one of these is the connection ID. So we try in terms of load balancing between threads, between processes, and a middle box. The idea is to have like completely stateless load balancing, as long as you can parse this connection ID. So it is an opportunity to have actually something better than we could have with TCP, where let's say a layer 4 load balancer or a kernel load balancer will have to maintain the state per connection. Instead, with Quick, it could be like completely stateless and route just based on this connection ID.
Got it.
I guess one other thing that like TCP does not have like graceful shutdown. If there's like graceful shutdown presence in transport, then it could really benefit these sort of zero downtime mechanisms. And with Quick, this can be possible. Got it.
So a couple of questions coming in on Slack. So Gianni Antici asks, why eBPF and not AFXDP? Just curious about your perspective on this.
From implementation perspective, eBPF has this thing called SO reuse port that Facebook has used over the years for doing some sort of L4 and L7 load balancing.
Right. What Usama pointed at is like let's say the version 2 of the work we had presented in this paper. It's actually not already deprecated, but we have a newer version that we have deployed recently at scale, and maybe we're gonna try to describe it for SIGCOMM next year. It's why not XDP? There are some trade-offs to be considered. For now, we went with a simple eBPF solution.
Okay.
But XDP is one of their candidates. Yeah.
Okay, so the last question, Anna Brunstrom asks, what if the Quick CID is changed by the client?
Yeah, so at Facebook, in our deployment, we do make sure that we route based on the server chosen connection ID. We have the ability to control both the client and the server, but we do not rely on that. So there are two connection IDs. There's the one that the client picks, and then there's the one that the server tells the client to use, and we use the server chosen connection ID to route.
Okay. Yeah. Thank you. Yeah. Go ahead.
Yeah, I think it's also part of Quick's specification that client cannot modify the server chosen ID.
Got it.
That was an interesting talk. While we wait for questions, can you tell us more about how this can be applied in other settings, for example, in cellular settings where there are issues like mobility?
Okay, so in case of cellular networks, I guess you're talking about the mobility from the client end.
Mm-hmm.
Yeah. So yeah, the similar sort of like reconnections can take place for like for cellular connections. But the point here is that to make the connection transition sort of transparent to the end user. So for example, in the case when there's client and we don't have any other downstream that you can use to maneuver any disruption, what Facebook relies on is to use things like HTTP go away to gracefully shut down a connection, or only shut down the connection when the connection is in idle phase, so that there is no disruption faced by the end user.
Mm-hmm. Yeah, we have a question on Slack from Polly. Interesting problem there, socket leak. How do you determine if a socket is no longer in use so you can garbage collect?
Yeah, so it's based on very like sort of low level implementation, but I think the important part here is that there should not be a socket that is sort of leaked. And that's why the monitoring strategy requires like taking a strict check on all the sockets available for listening TCP sockets or UDP sockets that are responsible for receiving any packets. I think Luca might add something here.
Yeah, so in the case we presented in the paper and that Osama talked about in the presentation, so if you have a leak for a socket, like the kernel will continue sending packets there. And so what you will see happening is that the queue for that socket will start overflowing. And that's why monitoring is important. There's no garbage collection. So if you pass a socket to another process and that process decide to not bind to it or not listen, there would be side effects.
Okay. And are there any applications or any settings where this way you cannot use this, or is this deployed across all data centers, all applications?
So currently, I don't think it's deployed across all the applications. There are a few where the sort of the ad hoc strategies are still being used. Because it's very focused on the protocols that do not have this graceful shutdown and that need additional support from infrastructure itself to sort of make the handover transparent.
Mm-hmm. Okay, I think that's all for the questions. Thanks to both of you.